So we've used Gauss's law to determine the electric field from a sphere, conducting sphere, and an infinite line of charge. Now let's continue on with the sheet of charge and plate of charge, and I'll distinguish between them as well. So here's a sheet. A sheet is really just an infinitely thin plane of charge, which means that the charges are unable to move through the thickness because it's infinitesimally thin. So it's just a layer, a single layer of charge. Now we're going to bring a Gaussian surface to this sheet and enclose some charge like this. Isn't that cool? Now I know you wish that the Gaussian surface itself, which is the coolest looking thing here, were actually the volume of charge, but well, sorry, it's not. But we'll have some cool looking volumes of charge to deal with as well, like a cylinder of charge. But anyway, right now, the charge is the sheet. It's infinitesimally thin, so it's just a single layer of charge. The end cap area is A. And we have an E field coming out of there. E field perpendicular to the sheet goes right through that end cap. And we're going to call that electric field E. It's in line with dA, right? It's perpendicular. And the other side has the same thing. Now the electric field through the cylinder wall, in order for an electric field to be going through this, or over here, it would have to be going, there'd have to be a component parallel to the sheet, which can't happen because the charges would move around until the electric field is zero in that dimension. So the electric field through the cylinder wall is zero. The flux enclosed by the end is E times A. Total flux through the surface then is double that for both ends. Now, the closed integral of E dot dA, the closed integral of E dot dA of the Gaussian surface, that's what this is equal to Q enclosed over epsilon 0. Well, how much does it enclose? It encloses just the amount that of the sheet covered there. And that is also, Q enclosed, the charge density times the area. So sigma A over epsilon 0, which is 2EA. So there we have it. The A's go away, and sigma over 2 epsilon 0, which we discovered before. That is the electric field from a sheet as determined by Gauss's law. And now let's move on to plates of charge. So we have two plates, and the difference between a sheet and a plate is a plate has finite thickness. So charges can actually move around on the other side if they so choose. Now if you have a plate charged up, these charges interact with each other so that all the charge, the surface charge density is distributed essentially on the inside as these charges attract each other. And there's essentially none on the outside. So the electric field, as we've already discovered, has a contribution from one sheet, or one plate in this case, and the other side. Now I say sheet here because it is just a single line of charge. Nothing's going on over on this side, and likewise the right side on the negative plate. So it's as though we have two sheets next to each other as a result of their interaction. Here's a Gaussian surface. We can put a Gaussian surface anywhere we want. This is a great place to put it. Well, yeah, because it's easy to analyze. Here we go. So this way, you might say, the flux through that side is EA. Well, yeah, that's true. But remember what E is? The electric field in a conducting material is always zero. So there is no flux there because the electric field is zero. The only flux passing through this Gaussian surface is the area on the right, this over here. Everything else is zero. And these plates I'm talking about where the charges really can move around, the only place they do that in a practical sense is on the end. Therefore it's called end effects. I didn't even show it here. Causes the electric field to be distorted, and it kind of makes loops at the very end. Moving on. So the flux through this Gaussian surface is Q enclosed over epsilon 0. EA, that's it. It's just through this side, not 2EA anymore. sigma A over epsilon 0 and sigma over epsilon 0, just like we had before. Totally consistent with our previously derived result of the contributions from one sheet, sigma over 2 epsilon 0, and the other sheet, sigma over 2 epsilon 0. There it is. Now let's consider the surface of a conductor. Here's our conductor. It's a conducting sphere. Radius r, charge q, and we'll put a Gaussian surface, plunge it through the material so some is coming out of the sphere itself. Area A, area vector in this direction, radially out, and the E field is all perpendicular. Wonderful. And that E field is kq over r squared because, as we've already discovered, a charged sphere looks like a point charge from the center. So at the edge, that is the electric field, kq over the radius of the sphere squared. Of course, everywhere inside it's 0 until we get to the outer edge, then it spikes up to that value. Now the surface charge density, what's that? Well, we know it's defined as charge per area, so let's do it over the whole thing. The whole charge is q, and the area is the area of a surface of a sphere, 4 pi r squared. So there it is. Oh wow, look at this and this. It's going to be that wonderful simplification that takes place here. Because q is sigma 4 pi r squared, and then the electric field is 1 over 4 pi epsilon 0 q over r squared. I love that. And there's our simple electric field, sigma over epsilon 0. Now for any conductor, actually let me just comment on that. So we saw that from a sheet, it's epsilon or sigma over 2 epsilon 0. The sigma over epsilon 0 occurred for a plate in the previous example. But we thought of it in the sense that the negative plate associated with that plate was contributing half of the electric field. Now we don't have another plate to double the sheet electric field and make it sigma over epsilon 0. But actually we do. Because on the surface you have this charge producing an E field. But think of everything going on over here. The collective contribution from the surface charge density everywhere behind the little region of the Gaussian surface. That's producing an electric field in such a way that the field inside here is everywhere 0. So it cancels this electric field. So it's the same size in the opposite direction. Well, all this contributes to that opposite direction as being outward. So this consists half of the charge right on the surface around here, and then the contribution from everything behind it contributes the other half. And so it really is as though we have two plates next to each other, essentially, functionally at least. And now for any conductor, some nebulous blob here, we have a Gaussian surface and perpendicular E field, and the shape can be anything you want it to be. The analysis that we had up here is the same analysis, but sigma varies in unique ways over the whole thing, but in such a way that the total, while the E field anywhere inside this thing is still always 0. So what I just mentioned about the E field here applies here just as well, just in perhaps more complex ways when you look at the details. So the different sigmas will affect the potential, but we haven't got to there yet. We'll be there soon. And now let's use Gauss's law to discover the E field in a uniformly charged insulating sphere. And in an insulating sphere, you notice the charges are not pushed all out to the outer edge. However we got this thing charged, think of it as a styrofoam ball perhaps. wherever those excess charges are, they're locked in place. So that's a uniform volume of charge in this case. That looks a little different. When we put a Gaussian surface inside this, little r, that Gaussian surface encloses charge. But since it's uniform charge density, then the electric field is radial everywhere on the surface of the Gaussian surface. And what's the surface area of that surface? Well, it's 4 pi r squared. Notice little r, we're talking about the Gaussian surface now, this region. Electric flux, sigma sub E is area times electric field. Well, the area is 4 pi r squared. The electric field is constant. At this point, we must introduce another term that's new, and that is volume charge density. You've had linear charge density, you've had surface charge density, but you haven't had volume charge density. So this is yet up another dimension. And, yep, it's rho. I don't know why. I'm just the messenger. So rho is the symbol. Let's go with it. It's not momentum, but it won't matter because when we're doing Gauss's law for volumes of charge, and if you're thinking momentum, what you really need to do is probably just go home and get another night's sleep, or a good night's sleep for a change. How's that? So charge over volume. The charge is Q. The volume is 4/3 pi r cubed for this whole thing. Notice big R here. So that's the volume charge density. So Q enclosed, we're talking about Q enclosed by the Gaussian surface, rho volume enclosed, which is rho times, what's the volume enclosed? Well, it's just 4/3 pi little r cubed, all right? Oh, but look at the wonderful cancellations. Yes, very good. Gives us Q, r cubed over r cubed. Small and big, of course. So that's Q enclosed. We're getting close. So the closed integral of E dot dA in Gauss's law is, in this case, this evaluates constant E. E is constant everywhere on the Gaussian surface. dA, you integrate that, you just get the area of the Gaussian surface. So that's E times 4 pi little r squared, which is Q enclosed over epsilon 0, according to Gauss's law. And that is, Q enclosed was this thing. So there it is, over epsilon 0. So finishing this up, we have the electric field is Q enclosed over epsilon 0A. Now, remember, EA, flux, bring the A up over here, is Q enclosed over epsilon 0. All right, but we've already got Q enclosed. Q enclosed was Q r cubed over r cubed. So this part is the Q enclosed. There's the epsilon 0, and there's the A, the surface area of the Gaussian surface. So the insulating sphere E field, QR, small r, over 4 pi epsilon 0, big R cubed. Remember, big R cubed is constant, or big R is constant. Little r is the variable. Let's go outside the insulating sphere now. So we'll just put a Gaussian surface on the outside of it. No problem. There it is. Radius little r. Q enclosed is Q. So the flux through the surface, which is EA, E times area, 4 pi r squared, is Q over epsilon 0. And we can just immediately write down what the electric field is. Q over 4 pi epsilon 0 r squared. It's as though all the charge were concentrated right here at the center, and we're looking at the E field at this surface, a distance small r away. So we're ready to map it, the E field that is. So between 0 and big R, between 0 and big R. That's the E field formula. What is it proportional to? And don't say inverse R cubed, because this is a constant. It's the radius of the sphere. It's really proportional to R. So not only is it not 0, like the E field inside a conducting sphere is, and not only is it some non-zero constant value, but it's actually growing. It's proportional to R. So there it is, and there's the value at the surface of the sphere, kq over r squared, like a point charge at the center. And then after that, it obeys this, which is just the regular inverse squared function. There it is. E is continuous, unlike for a conducting sphere where it's 0, and then it spikes up here, and then follows that same inverse square law pattern.